Welcome back to the deep dive. This is where we really dig into complex systems, not just scratching the surface, but getting down to the fundamentals to pull out knowledge you can actually use.
Glad to be back.
Today, we are immersing ourselves in, well, arguably the single greatest geological sculptor on the planet, the river system.
Absolutely. They shape so much of our world.
When you look at a river, it's so much more than just that blue line you see on a map, right? You're looking at a force that, as our sources really stress, carves away billions of tons of material from the land every single year.
Billions. It's an incredible amount of work being done.
And rivers are, the main arteries of the whole hydrologic cycle. They carry the vast majority of fresh water from the continents back to the ocean.
It's a primary return path.
So our mission today is focused on let's call it the integrated management and planning of this huge dynamic system. We need to synthesize the complexity of how rivers work, from defining the tiniest channel, which I learned is called a rill, all the way up to these massive structures like floodplains and deltas.
From the very start to the very end of the journey.
And crucially, we also have to understand the challenges engineering, economic planning involved when we try to manage that immense power, especially when that water decides to leave its banks.
Which it inevitably does.
So whether your interest lies in geography, civil engineering, maybe environmental planning, or even if you just want to really grasp the forces shaping the world around you, this deep dive into stream flow, channel types, and flood response, well, it's going to give you some essential insights.
Definitely.
Okay, let's dive in. Let's unpack the system right from the beginning.
Right. It's a system built on, well, fundamentally simple rules. Gravity, mostly.
Yeah.
But it ramps up in complexity incredibly quickly.
Okay.
So first off, just getting the language right. We use the general term river, sure. But our sources point out that smaller flows can be called streams, creeks, brooks, rivulets, or even right at the very start, rills.
Rills, okay.
They're all essentially the same thing, though. Flowing freshwater courses, just different scales.
Got it. So how does this whole system fit together, the architecture of it?
Yeah, the river system architecture. You can think of it like a vast network, maybe like a tree, or even the circulatory system in a body.
All right.
It's defined by the direction of flow.
Okay.
Most importantly, you've got the tributaries. These are all the smaller rivers and streams, like the smaller veins, maybe that flow into a main river channel. They feed it, constantly adding water, increasing its volume.
So they gather the water.
Exactly. The main river plus all its tributaries, that makes up the complete drainage network for a specific area, what we call a watershed or catchment basin. It's the collection phase. Water's being drawn inwards.
But it's interesting, the river doesn't just collect water, does it? It also spreads it out.
That's right. Particularly near the river's mouth,
Yeah.
where things flatten out, maybe in delta regions, we often see distributaries.
Distributaries, okay, the opposite.
Yeah, these are streams that actually branch off and flow away from the main channel. It's an outward distribution, not the inward collection you see upstream.
Ah,
So if you like the body analogy, tributaries are the veins bringing blood back to the heart, and distributaries are more like the capillaries, spreading it out at the very end.
I like that. It really highlights that this is a dynamic responsive system.
Yeah.
So how do we actually measure that response, the flow itself?
Right, the stream flow response, that's the actual volume and speed of water you measure at any given point.
Yeah.
And it's highly integrated. It reflects everything happening upstream, both across space and over time.
Integrated, meaning it's not just one thing.
Exactly. It's determined by three key interconnected factors that really describe the whole catchment area.
Okay, what are they?
First, the obvious one, input rates. How much water is actually hitting the ground? Rain, snowmelt. This varies hugely, of course, depending on where you are and when. A quick local thunderstorm versus a long, slow regional rain are very different inputs.
Makes sense. Input. What's second?
Second is the travel time from the watershed surface to the stream network. This is how long it takes a drop of water once it hits the ground to actually make its way into a defined stream channel.
Ah, so how quickly it runs off versus soaking in.
Precisely. And this time is heavily influenced by the landscape itself. The length and steepness of the hillsides. The vegetation-covered trees, grass, they act like sponges and add friction, slowing things down, letting water infiltrate.
Right.
And then the soil type and the underlying geology. How porous is it? How much soaks in versus running straight off?
Okay, so input, surface travel time. What's the third?
The third factor is the travel time within the channel network itself, down to the point where you're actually measuring the flow. Once the water's in a channel, its speed depends on the total distance it has to travel and, well, the nature of that channel. Is it a straight shot, Or is it all winding and full of obstacles?
So all three, the input, the journey over the land, and the journey in the stream combine to give you that final flow reading.
Exactly. They all get synthesized into that single measurement of stream flow. It tells a story about the entire watershed above that point.
That's a really clear framework. But here's where the source material introduces something I found fascinating, a sort of mathematical elegance to it all. The idea of stream order.
Ah, yes, stream order. It's a classic concept in hydrology.
It seems like a really neat way to classify the hierarchy, the structure within this branching network. It gives you a number, a quantitative measure of the network's complexity.
It does. Developed back in the mid-20th century and still very useful.
So how does it work? How do you assign these orders?
You start right at the top, the very beginnings of the flow. First-order streams are the smallest ones, the headwater channels. The key thing is they have absolutely no upstream tributaries feeding into them. They're just collecting initial runoff.
Okay, the absolute starting points, first order.
Then the order only increases when two streams of the same order come together. So a second-order stream is formed only when two first-order streams join.
Only when two of the same order meet.
Got it. And it continues logically. A third-order stream needs two second-order streams to merge. And so on. You know, huge river systems like the Amazon can get up to orders of 12, maybe even higher.
Wow. Okay, that seems straightforward enough. Two firsts make a second, 2 seconds make a third.
But here comes the crucial rule. The one that sometimes trips people up because it feels a bit counterintuitive.
Okay.
The intersection of a higher-order stream with a stream of a lower order does not raise the order below that junction.
Hang on. So if you have, say, a big fourth-order stream and a tiny little first-order stream flows into it,
The stream below that point remains fourth order.
it doesn't become fifth order.
Nope. Think about why. That rule ensures the order number truly reflects the overall scale and complexity of the entire upstream drainage network. It's not just about counting junctions.
Ah, I see. If every little trickle bumped up the order, the numbers would become meaningless very quickly, especially in big systems.
Exactly. That little first-order stream, in the grand scheme of the fourth-order system's drainage area, is almost negligible in terms of contributing network complexity. The order reflects the cumulative power built up by merging significant branches.
It's like adding a twig to a main branch versus grafting two main branches together. Only the latter really changes the fundamental structure. That's a really key point for understanding these systems.
It is. It quantifies the network structure in a consistent way.
Okay, so we've got the basic architecture, the flow response, and this ordering system. Let's move into section 2, where we start classifying the different personalities rivers can have. Because, as the sources highlight, they aren't all the same. They vary based on what they flow over, their connection to groundwater, and how consistently they flow.
Right. These three classification methods give us a much richer picture for understanding and managing a specific river. We look at the nature of the substrate, what's the riverbed made of? Their relationship to the groundwater table, is the river feeding the ground, or is the ground feeding the river? And the percentage of time they flow.
Let's start with the substrate. What's the difference there?
We distinguish between bedrock rivers, sometimes called non-alluvial. These flow directly over solid, exposed bedrock. They tend to carve down very slowly, mostly by abrasion, grinding away with the sediment they carry.
So slow and steady erosion, often in canyons.
Often, yes. Then you have alluvial rivers. These are much more dynamic. They flow on a bed made of sediment, sand, gravel, silt that the river itself has deposited. And crucially, it can pick up that material again, move it, redeposit it. The alluvial river is constantly reworking its own bed and banks.
So it's flowing on its own leftovers, essentially, and can reshape them.
You could put it that way, yeah. It's in constant dialogue with its own deposits.
And this ability to self-modify, that connects to the second classification, right? The groundwater connection.
Yeah.
This seems really practical for planning. Is the river a giver or a taker of water from the ground?
Absolutely critical distinction. We talk about influent versus effluent rivers. An influent river is often called a losing river. You see these more in arid or semi-arid climates. In this case, the water surface in the river is actually higher than the local groundwater table in the surrounding banks.
Higher in the river,
So because water flows downhill or down gradient, the river water seeps out into the banks and downwards, recharging the aquifer. It's losing water to the ground.
So an influent river is literally feeding the groundwater. If you dam it up or take too much water, you're directly impacting groundwater levels.
Precisely. It's a direct contribution to the groundwater reserves.
Okay, so what's the opposite? Effluent.
Right. An effluent river is a gaining river. more typical in temperate or humid regions. Here, the water surface in the river channel lies below the level of the groundwater table in the adjacent banks.
Below, so the groundwater is higher.
Yes, which means the groundwater seeps into the river channel. The river gains water from the surrounding aquifer. This groundwater contribution is what keeps many rivers flowing even during long dry spells, well after the last rain. It's sustained by those underground reserves.
Understanding influent versus effluent seems absolutely fundamental for any kind of water management or, say, deciding where to put wells. The implications are huge.
Huge. Knowing if your river depends on groundwater or replenishes it changes everything.
Okay, and the third classification was about flow persistence. How often does the river actually have water?
Yeah, this is vital for ecology, for infrastructure, knowing if water will be there reliably.
Makes sense.
We define perennial streams or rivers as those that flow all the time, year-round, even long after the last rain, because they're usually effluent, sustained by that groundwater base flow.
Okay, perennial means always flowing.
Then you have intermittent or seasonal streams. These might flow like perennial streams during the wet season, but they dry up completely during the drier part of the year. Their flow reflects climate shifts or a stronger dependence on recent rainfall rather than deep groundwater.
So on and off with the seasons.
Exactly. And finally, there are ephemeral streams. These are very short-lived. They only flow for a brief period right after a rainstorm. They're basically just surface runoff channels. Their beds are dry most of the time. Think desert washes or arroyos.
Got it. Perennial, intermittent, ephemeral, all based on how long the water sticks around.
Correct.
Now, moving from the flow itself to the river's actual shape in the landscape, let's talk sinuosity. It sounds technical, but it's just about how curvy the river is, right? How much it snakes back and forth.
Pretty much, yeah. Sinuosity is a measure of the channel's curvature. It's generally related to the river's energy, specifically its screen flow power, which is basically slope times the amount of flow. More power often means a straighter course. Less power allows more wandering.
And we can quantify this. Give it a number.
We can. The sinuosity index is the ratio of the channel length to the straight line valley length.
Yeah.
If that ratio is close to 1, we call the channel straight. Though, truly straight natural channels are rare over long distances.
Okay, 1 is straight niche. What about curvy?
If the sinuosity index gets to 1.4 or higher, we officially classify it as meandering. It's definitely weaving now.
1.4 for meandering. And really curvy.
If it hits 2 or more, we call it tortuous. That means the river channel is at least twice as long as the valley it's flowing through. It's doubling back on itself quite a bit.
Straight, meandering, tortuous. Okay.
And those shapes, combined with where they occur, lead us to the 4 main channel plan forms described in the sources. These reflect that balance between water energy, the sediment it's carrying, and the surrounding landscape.
What are the main types?
First, those straight channels. Again, rarely perfectly straight, but they tend to occur near the headwaters, or where a river is cutting through a narrow canyon or across a resistant ridge. The landscape basically forces it into a relatively straight path.
Confined.
Second, and visually quite striking, are braided streams. You see multiple channels constantly splitting and rejoining. That's called anastomosis. This creates these shifting islands or bars of sediment, usually gravel and sand, in between the water paths.
Right, looks like braids of hair almost. Where do you typically find those?
Usually where you have 2 things, a steep gradient, so high energy, and a very large amount of coarse, poorly sorted sediment being dumped into the system. Think of rivers coming right off melting glaciers or flowing out of high mountains. They drop so much debris, the water has to constantly find paths around it.
Steep slope, lots of rocks. Got it. What's next?
Third is probably the image most people have when they think river, the meandering stream. These wander in those big, looping curves across a wide, flat floodplain, characteristic of low-gradient environments, lowlands, where the river has the energy and the space to move sideways, eroding the outer banks of bends and depositing on the inner banks.
The classic snake-like river.
Exactly. And finally, though we touched on it as a depositional feature, it's worth mentioning the alluvial fan again here as a kind of channel transition type.
Right, where the mountain stream hits the flat plain.
Yeah. Unlike a meandering stream developing slowly on a low slope, the fan is formed by that sudden, drastic drop in slope and velocity. High-gradient mountain stream hits a flat valley floor, loses energy instantly, and just dumps its sediment load in that characteristic cone or fan shape. The geometry is dictated purely by that abrupt change.
That discussion of slope, velocity, sediment, it perfectly sets up Section 3, the river's geomorphological toolkit, how it actually reshapes the land. The nuts and bolts of erosion, transport, and deposition.
Right, the core mechanics. It all starts with two fundamental processes, erosion and sedimentation.
Okay.
Erosion is the wearing away part. Water flowing over the ground or within the channel picks up and washes away soil and rock particles. How much erosion happens depends on a lot of things. Slope steepness, obviously. Vegetation cover plants hold soil together. The type of soil itself is easily washed away. And climate factors, like how hard the rain is falling.
So picking stuff up and sedimentation is putting it back down.
Exactly. It's the flip side. Those eroded particles get carried along until the water slows down enough or the environment changes, so it can't carry them anymore. Then they settle out. Deposition. This happens typically where velocity drops like the inside of a river bend, or where a river flows into a lake or the ocean. It's mostly driven by stream characteristics like slope, but especially flow velocity and the overall discharge.
Okay, erosion takes, sedimentation gives. Now, what is the river actually carrying, the sediment load? It's not all the same stuff, is it?
No, not at all. The sources classify the sediment load based on how it's transported. This tells us a lot about the river's energy.
That's so.
Well, first, there's the dissolved load. This is material that's completely dissolved in the water, like salts and minerals. You can't see it. It gives river water its chemical fingerprint, but it's invisible transport.
Okay, dissolved, like sugar in pee.
Kind of, yeah. Then you have the suspended load. This is the fine stuff. Clays, silts, maybe some very fine sand. These particles are physically held up within the water column by the flow's turbulence. This is what makes a river look muddy or cloudy.
Right, the visible dirt in the water.
Exactly. And finally, there's the bed load. This is the heavy artillery. Coarse sand, gravel, pebbles, cobbles, even boulders in flood conditions. This material is too heavy to be suspended, so it moves along the river bottom by rolling, sliding, or bouncing, a process called siltation.
So the bed load is what really does the grinding and shaping of the channel floor.
Absolutely. It's the abrasive tool, and it takes the most energy to move.
Which brings us to the river's strength. The sources make a distinction between capacity and competence. They sound similar, but they're different.
Very different, and it's a crucial distinction. Capacity is about quantity. It's the maximum total load, the total weight or volume of sediment that a stream can transport. Think of it as the river's overall carrying power. It's strongly related to the total volume of water flowing discharge.
Okay, capacity is how much total stuff it can move.
Right. Competence, on the other hand, is about size. It's the maximum size of an individual particle that a stream can transport. Think of it as the river's lifting power. This is more related to the velocity and turbulence of the flow.
Can you give an example to make that clearer?
Sure. Think of a huge, wide, slow-moving river near its mouth, like a lower Mississippi. It has enormous capacity. It moves millions of tons of fine silt and clay every year, a massive total load. But because it's flowing slowly, its competence is very low. It can't pick up, say, a baseball-sized rock.
Okay, high capacity, low competence.
Now, contrast that with a small, steep, fast-flowing mountain stream during a flash flood. Its total capacity might be relatively small. It's not moving a huge volume of material overall, but its high velocity gives it incredibly high competence. It can roll huge boulders down the channel, things the Mississippi couldn't budge.
Ah, okay. Capacity, total amount. Competence, biggest piece size. Got it.
And that interplay dictates where sediment actually gets deposited within the channel. The general term for any accumulation of coarser sediment inside the channel is just a bar.
Just a bar. Okay.
But they get more specific names depending on where they form. On the inside bend of a meander, where the water slows down, the deposited sand and gravel form a point bar.
Point bar on the inside curve. Makes sense.
In those braided streams we talked about, the bars are much larger, often elongated in the direction of flow, and they're strong enough to actually split the flow. We call those braided bars or sometimes longitudinal bars.
Okay. And this whole cycle of erosion on the outside bend, deposition on the inside, that's what drives meandering, right? The river literally eats away at one bank and builds up the other.
Precisely. And this process is most obvious in the fascinating life cycle of a meander loop. A meander isn't static. It migrates across the floodplain over time, and it leaves behind very clear evidence of its past movements.
Like geological footprints.
Kind of, yeah. As the river shifts, you can sometimes see subtle, curved ridges and troughs on the floodplain, parallel to the old meander bends. These are called meander scrolls. They mark where the channel used to be.
Okay. Traces of old paths.
Now, as a meander loop gets more and more exaggerated, the neck of land between the start and end of the loop gets narrower and narrower. Eventually, often during a flood, the river finds a shortcut. It cuts a new, shorter channel straight across this neck. This new channel is called a chute.
A chute, like a shortcut.
Exactly. And the chute rapidly captures more and more of the flow because it's steeper and more efficient. Eventually, it becomes the main channel.
And what happens to the old big loop?
The old loop gets cut off. This abandoned meander loop is called an oxbow.
The oxbow, right.
If the water table is high enough, or if it gets periodically refilled by floods, this U-shaped oxbow remains filled with water, forming an oxbow lake. You see these all over mature floodplains.
That distinctive U shape.
And finally, over time, sediment deposition tends to seal off the ends of the oxbow, where it used to connect to the main river. This wedge of sediment that blocks the entrance is called a clay plug.
Wow. So meander scrolls, chute, oxbow, oxbow lake, clay plug. It's a whole story written on the landscape over, what, decades? Centuries?
Depending on the river, yeah, it can happen relatively quickly in geological terms. It's a dynamic process.
And all this wandering back and forth, depositing sediment during floods, that's fundamentally how the floodplain itself is built, right? That wide, flat valley floor next to the river.
Absolutely. The floodplain is the river's construction project, built layer by layer from flood deposits and the remnants of its own sideways migration.
Looking sideways then, across the floodplain during a flood, what features do we see?
Well, during floods, as the water spills out of the channel, it rapidly loses velocity right at the edge. This causes the coarser sediment, sand and silt, to deposit right next to the channel, building up ridges along the banks. These are called natural levees.
Natural levees, built by the river itself.
Yes. They slope gently away from the river. Now, if a flood is big enough to breach or break through this natural levee, the water rushes out carrying coarser sediment, which then gets deposited in a fan or delta shape out on the floodplain. That deposit is called a splay.
A splay. Okay, like a breach deposit.
And sometimes these natural levees can act like low dams, trapping floodwater in depressions further out on the floodplain. These areas can stay wet long after the main flood recedes, forming back swamps. These are often important wetland habitats.
Natural levees, splays, back swamps. The floodplain has its own topography. Now, for planning, how do we technically define the floodplain? Is it just where it floods?
It's a bit more precise than that, especially for regulation. The sources distinguish between the hydrologic floodplain and the topographic floodplain.
Okay, what's the difference?
The hydrologic floodplain is the land immediately next to the normal base flow channel. It's the area that gets inundated relatively frequently, basically anytime the water rises above the bank full stage, the point where it just starts to spill out.
So the frequently flooded zone right next door.
Right. The topographic floodplain is much broader. It encompasses the hydrologic floodplain, but extends outwards and upwards to the maximum elevation that would be reached by a flood of a specific, usually large magnitude or recurrence interval, like the area inundated by the 100-year flood. This wider definition is typically what's used for zoning and development regulations.
That makes sense. One is about frequent nuisance flooding, the other about major hazard mapping.
Precisely.
Now, before we dive headfirst into floods themselves, let's quickly touch on how this physical structure affects life in the river. The sources talk about the river continuing concept.
Yeah, the idea is that the physical characteristics of the river change predictably from headwaters to mouth, and the biological communities adapt along that gradient.
How does that work? What's it like at the start?
In the early stage, the headwaters, the stream is typically narrow, maybe steep, and often shaded by dense forest cover. Less sunlight reaches the water. So there aren't many primary producers, like algae, that need sunlight.
Okay, low light. So what do things eat?
The energy base comes mostly from outside the channel, fallen leaves, twigs, insects dropping in. So the aquatic life is dominated by heterotrophs, organisms adapted to shredding or collecting this imported organic detritus, things like certain insect larvae, crustaceans.
So eaters of imported stuff, what happens further downstream?
As you move into the mid-level reaches, the channel typically widens, the gradient lessens, more sunlight gets in, the water warms up more. This allows for more primary production algae, rooted aquatic plants. You get a greater variety of life, including grazers that eat the algae and predators that eat the grazers and shredders. It's a more diverse community.
More light, more local food production, more diversity.
Okay.
And then the lower reaches, near the mouth.
By the time you get to the lower reach, the river is usually wide, slow-moving, and carrying a lot of fine sediment washed in from the entire upstream watershed. This makes the water much more turbid or murky.
Huh. So less light penetration again.
Potentially, yes. The high turbidity can limit light for photosynthesis, shifting the food web again, perhaps more towards organisms that filter fine organic particles from the water column, or bottom dwellers. The point is, the physical setting dictates the biological community all the way along the river's course. What happens upstream affects life downstream.
That's a great illustration of the river as an interconnected system, which brings us inevitably to Section 4. When the river overflows, floods. This is critical because, as we said, humans love to build on floodplains, putting us directly in harm's way.
It's the fundamental conflict.
So, simply put, a flood is just when the river's discharge gets so high it can't stay within its banks and spills out onto floodplains.
That's the basic definition, yes. Unusually high flow exceeding channel capacity.
And to manage this, we need to talk about magnitude. Floods aren't all the same size. The sources use the concept of recurrence interval.
Right. Recurrence interval, or return period. It's a statistical measure. Bigger, more severe floods happen less frequently than smaller ones. The recurrence interval is the average time between floods of a given severity or greater, based on historical data for that specific river.
So the 100-year flood, that's the key one everyone talks about. What does that actually mean? Does it happen exactly every 100 years?
No, absolutely not. That's a common misconception. A 100-year flood level means there is a 1% chance, 1 in 100, of a flood reaching at least that magnitude occurring in any given year.
Ah, okay. It's a probability thing each year, not a schedule. You could have 2 100-year floods in consecutive years, theoretically.
Theoretically, yes. Or you could go 200 years without one. It's just the long-term average probability.
Got it. So what causes these unusually high discharges? What are the mechanisms behind floods?
We fall into a couple of broad categories. First, you have hydrometeorological floods. These are directly linked to weather and climate.
Like heavy rain.
Yeah, things like rapid snowmelt runoff, especially in spring. Intense, prolonged storm rainfall. Sometimes a nasty combination, like heavy rain falling on existing snowpack, rain-on-snow events, which can release a lot of water very quickly. Or physical blockages like ice jams forming in rivers during winter or breakup.
Okay, weather-related. What's the other category?
The other main driver is natural dam failures. This is when a natural event, like a huge landslide or a glacier advancing, blocks a river valley, forming a temporary dam. Eventually, that natural dam fails, either overtopping and eroding or collapsing catastrophically. This releases the huge volume of water stored behind it very suddenly. These are often called outburst floods, and they can be incredibly destructive.
Wow, a sudden wall of water from a failed landslide dam. Terrifying.
Very. And on top of these direct causes, we always have to remember other factors that influence how severe a flood becomes. Things like the regional climate patterns, the underlying geology, how quickly can water soak into the ground, and critically, human land use.
How does land use play in?
Big time. Deforestation in the headwaters reduces the landscape's ability to absorb and slowly release rainfall, leading to faster runoff and higher flood peaks. Urbanization, replacing forests and fields with pavement and rooftops, does the same thing. Water runs off immediately into storm drains and rivers instead of soaking in. These changes can significantly worsen flooding downstream.
Right, so for engineers and planners trying to design bridges, dams, levees, they need specific flood numbers to work with, right? Not just probabilities.
Exactly. They need concrete design targets. The sources outline 4 key types of design floods used in water resource management.
Okay, what are they?
First is the Standard Project Flood, or SPF. This is an estimate of the flood you'd expect from the most severe combination of weather and hydrological conditions that are considered reasonably possible for that specific river basin. Importantly, it generally excludes the absolute most extreme, rarest catastrophic events.
So, really bad, but not the absolute worst imaginable. What's it used for?
It's often used for designing structures where failure would be serious, but maybe not utterly catastrophic, like levees protecting agricultural land or spillways for smaller dams.
Okay, what's bigger than the SPF?
That would be the maximum probable flood, or MPF. This one does try to encompass the extremely rare, most severe flood theoretically possible. It represents the upper limit of what could conceivably happen, considering the most extreme meteorological and hydrological factors.
The absolute worst case. When would you design for that?
Almost exclusively for the spillways of very large, high-hazard dams located upstream of major population centers. Because the consequences of such a dam failing are so unthinkable, the economics kind of go out the window, and ensuring it can pass the absolute maximum possible flood becomes paramount.
Right. Safety overrides cost in that case. What else?
Third, there's the concept of probable maximum precipitation, or PMP. This isn't a flood estimate directly, but an estimate of the greatest depth of rainfall meteorologically possible for a given duration over a particular drainage basin.
The worst possible rainstorm. How do they figure that out?
It's complex. They often use a method called storm transposition. They take the data from the most severe storm ever recorded elsewhere, maybe in a region with similar climate and topography, and then mathematically transpose or move that storm over the basin they're studying, adjusting for moisture availability, elevation, and other factors to estimate the physical upper limit of rainfall for that specific location.
Wow, that's like a worst-case weather simulation, taking a real monster storm and dropping it on your area.
Essentially, yes. It's a way to estimate the maximum possible input. This PMP value is then often used in hydrological models to calculate the resulting maximum probable flood, MPF.
Okay, SPF, MPF, PMP, what was the fourth?
The fourth is simply the generic term, the design flood. This is the actual specific flood magnitude, whether it's an SPF, an MPF, or maybe a flood with a specific recurrence interval like the 100-year or 500-year flood, that is chosen for the design of a particular structure, a bridge, a culvert, a levee. The choice depends on balancing the level of protection needed against the cost of providing it.
Right, the final choice based on risk and budget.
Yes, exactly.
Now, to make this less theoretical, the source material uses the tragic example of monsoon floods in South Asia to show how these factors combine in the real world. It points to several compounding causes there.
It's a devastatingly clear example of complex interactions.
One is obvious: the monsoon itself. Intense, prolonged seasonal rains falling over huge, densely populated river basins and deltas where the water simply has limited places to go quickly.
The sheer volume of water input is staggering.
Two, a major contributing factor is widespread deforestation on the hill slopes and the headwaters, particularly in the Himalayas. Removing those forests drastically reduces the land's capacity to soak up rain and release it slowly.
So the runoff is faster and more intense, leading to higher peaks downstream.
Three, the sources mention the ongoing silting up of river channels. This is often linked to increased erosion from agriculture and the effects of irrigation systems. As channels fill with sediment, their capacity to carry water is reduced.
Meaning they overflow their banks more easily at lower discharge levels.
And fourth, there's the overlay of global warming. This seems to be accelerating the melt of Himalayan glaciers and snowpack, adding more water to the rivers, particularly during certain times of the year, and adding a layer of unpredictability to the whole system.
It's a potent and tragic mix. Extreme natural rainfall, human alteration of the landscape reducing storage, channel capacity shrinking, and climate change potentially adding more water unpredictably.
It perfectly illustrates why Section 5, dealing with flood control and the economics of protection, is such a massive and complex challenge.
Absolutely, because you're fighting immense natural forces, often exacerbated by human actions, and you have limited resources to do it.
So we need those design flood magnitudes. SPF, MPF, 100-year whatever is chosen because they dictate how big our defenses need to be. Spillways, reservoirs, flood banks. Everything depends on that target level of protection.
That's the starting point for any intervention.
We try to minimize flood damage using a mix of approaches. There are the hard structural engineering solutions and then the soft non-structural approaches like planning and zoning. Let's tackle the structural ones first, the ones designed to physically control the water.
Okay.
Flood control measure 1 is basically confinement. The most common way to do this is building levees. You might also hear them called flood banks, dikes, or sometimes concrete flood walls. The idea is to build walls along the river to keep the flow within a defined corridor, protecting the land behind them.
The classic flood defense. Build a wall.
But it's not that simple, is it? Building levees has major consequences for how the river behaves within those walls. The sources highlight 4 key effects.
Yes, confining a river changes its dynamics significantly.
First, levees increase the rate of flow. The water moves faster because it's squeezed into a narrower channel.
Right, higher velocity.
Second, because the water can't spread out, the floodwater level, the elevation or crest, gets higher for the same amount of discharge.
Higher and often faster rising water levels between the levees.
Third, this concentration of flow increases the channel's sediment carrying capacity.
It can move more material.
And fourth, maybe most importantly, the faster flow increases the scouring action. The river erodes its own bed and banks much more aggressively between the levees.
It tries to dig deeper in response to being squeezed sideways. This can actually undermine the levees themselves over time if not managed carefully. It's a feedback loop.
So levees solve one problem but create others. What's the next structural approach?
Flood control measure 2 is channel improvement. This involves actively modifying the river channel itself to make it carry water away more efficiently. basically increasing velocity and reducing friction or roughness.
How do you do that? Dredging.
That's part of it. Removing sandbars, clearing up vegetation from the channel banks, removing fallen trees or other large debris that obstructs flow, making the channel smoother and clearer.
Okay. Anything else?
A major and sometimes controversial technique under channel improvement is creating meander cutoffs. This is where engineers deliberately cut a straight channel across the neck of a sharp river bend.
Like we discussed with chutes forming naturally, but doing it on purpose.
Exactly. It shortens the river's path, which increases the slope, boosts the velocity significantly, and gets the floodwater out of that area much faster. It also means you need shorter lengths of levee, potentially saving costs. But it dramatically changes the river's character.
And leaves behind another oxbow lake, presumably.
Often, yes.
Okay, so confinement with levees, channel improvement. What else?
The third strategy is diversion. Sometimes you accept the main channel just can't handle the biggest floods. So you design ways to divert some of that excess water away from vulnerable areas, often into specially constructed bypass channels or designated floodways, which might be agricultural land or natural lowlands allowed to flood.
Diverting the flow? How does that work?
One interesting technique mentioned is the fuse plug levee. This is a section of the main levee system that is intentionally designed to be lower or weaker than the rest.
Designed to fail. Why?
Yes. When the flood reaches a specific, predetermined high level, this fuse plug section is designed to wash out relatively easily and quickly. This breach then acts like a controlled spillway, diverting a large volume of water into the designated floodway, relieving pressure on the main levees, protecting more critical areas, like a city downstream.
Wow, an engineered weak point as a safety valve? That's clever, but must take careful planning.
Extremely careful hydraulic modeling and design, yes, it's a calculated sacrifice.
Okay. And the fourth structural measure.
Measure 4 is temporary storage. Building structures specifically designed to hold back floodwater temporarily. The most common are upstream reservoirs, dams, but also retarding basins or detention ponds. Their main job is to capture the peak of the flood inflow and release it downstream much more slowly, at a rate the downstream channel can handle without flooding.
So smoothing out the flood peak.
Exactly. Flattening the hydrograph, as hydrologists say.
Are there downsides to storage?
The main risk, highlighted in the sources, is one of timing. You have to carefully design the release rate from the storage basin. If you release water at the wrong time, it might arrive downstream just as a flood peak is coming down from another, uncontrolled tributary.
So the two peaks could combine and make the flooding downstream even worse than if the storage basin wasn't there.
It's a potential synchronization problem that requires very careful operational planning, considering the whole river network.
Right. Okay, those are the big structural approaches: levees, channel work, diversion, storage. Now what about the non-structural side, moving away from concrete and earthworks?
This is where planning, policy, and land management come in. Measures 5, 6, and 7 focus on land management and zoning.
How does managing land help with floods?
Well, upstream, in the watershed, implementing soil conservation practices on farms can make a difference. Things like contour plowing or bunding, terrace cropping on slopes, building small check dams and gullies. These all help slow down runoff near its source and encourage infiltration, reducing the amount of water that reaches the river quickly.
Okay, small actions adding up across the landscape.
Then there's planning for evacuation, having warning systems and plans for getting people out of harm's way temporarily. And, more permanently, using legislation to implement floodplain zoning. This means using those flood maps we talked about to restrict or control what kind of development is allowed in different risk zones, maybe prohibiting residential building in the most dangerous areas, for example.
So keeping people and vulnerable infrastructure away from the flood zones in the first place.
That's the goal. We also see flood-proofing of individual properties. This is where you take measures on a specific building to protect it, even if it's in a flood-prone area.
Like what? Stilts.
That's one way, elevating the building on pilings or landfills. Or you could build a small ring levee or flood wall just around the property itself. Or design basements and lower floors with watertight walls and seals to keep water out. It's adapting the structure to the risk.
This really highlights a key distinction the sources make: protection versus regulation.
Yes. Protection refers to the hard engineering works, dams, levees, channelization, trying to physically stop the flood. Regulation is the soft approach, mapping the hazard, using zoning laws, requiring flood insurance, maybe doing upstream abatement like reforestation or restoring wetlands to help soak up water naturally.
So regulation is more about living with the flood risk intelligently rather than trying to eliminate it entirely.
Often, yes. It's about managing the risk and the consequences, acknowledging that floods will happen.
You mentioned channelization earlier as a structural measure. The sources point out a paradox with it, using the San Diego River as an example.
Right. The paradox of channelization. When you straighten, deepen, and maybe line a river channel with concrete, it definitely makes the water flow through that specific section much faster and more efficiently. It reduces local flooding there.
Sounds good. What's the paradox?
The consequence is that you're essentially creating a high-speed chute for the floodwater. So for a given amount of rainfall upstream, the channelized section delivers a higher peak discharge downstream and delivers it faster.
Ah, so you solve the problem locally, but you potentially make it worse for whoever is downstream.
Exactly. You accelerate and concentrate the flood wave. It often shifts the problem rather than solving it for the whole system. It can be a classic case of unintended consequences, sometimes driven by localized needs or politics.
This really underscores the need for careful management of the entire floodplain and the floodway. Can you remind us of the difference again?
Sure, the floodplain is the whole area that's generally prone to flooding. The floodway is the critical part within the floodplain, essentially the main channel plus the adjacent area that must be kept clear to allow floodwaters to pass through without causing a dangerous rise in water levels upstream.
So the floodway is like the absolute minimum corridor the river needs during a major flood.
Yes. Development in the floodway is usually highly restricted or prohibited altogether. Managing the floodplain involves detailed hydraulic modeling to understand how any proposed development in the wider floodplain, the flood fringe, might affect flood levels, ensuring it doesn't worsen the hazard for others. It's about building community resilience while respecting the river's space.
Now, all these measures, structural or non-structural, they cost money. A lot of money. The sources stress that this all has to be grounded in flood control economics.
Absolutely. You can't just build infinitely high levees everywhere. Protection has to be justified, usually through some form of cost-benefit analysis.
Is there a rule of thumb for deciding how much protection is worth it?
A key one mentioned is that providing protection against extremely rare floods, say, the 500-year or 1,000-year event, is often found to be uneconomical. The enormous cost of building defenses that high usually outweighs the projected benefits, given how infrequently such events occur.
So you don't usually design for the absolute worst imaginable flood, unless it's like that high-hazard dam situation.
Generally, no. The design flood level chosen for most projects is typically the one where the ratio of the expected annual benefits of protection to the annualized cost of providing that protection is at its maximum. You're looking for the sweet spot, the best return on investment in terms of damage reduction.
Okay, let's break down those costs and benefits. What goes into the costs?
The obvious one is the initial capital cost, building the dam, the levee, whatever it is. But you also have to factor in the interest paid on the money borrowed to build it, funds set aside for major repairs or replacement eventually, a sinking fund, and crucially, the ongoing annual costs of operation and maintenance. Levees need inspecting and repairing, reservoirs need managing.
Right, it's not just a one-time cost. What about the benefits? How do you calculate the value of not flooding?
This is harder, especially putting dollar values on everything. The sources divide benefits into two types, direct benefits and indirect benefit.
Okay, direct sounds easier.
Relatively. Direct benefits are the damages directly avoided because of the protection. So, damage to buildings, roads, infrastructure that doesn't happen. Losses to crops or livestock that are prevented. Prevention of disruption to transport and communication networks. Avoiding the immediate costs associated with loss of life and injury, though valuing life is inherently difficult.
Okay, avoided physical damage and disruption. What are indirect benefits?
These are the knock-on effects, often harder to quantify. It includes things like money saved on government relief payments or private insurance payouts that are no longer needed. Potentially higher agricultural yields or land values in the protected area because the flood risk is reduced, allowing for more intensive or higher value use.
Makes sense. Higher productivity.
And a really important one, the reduction in public health costs associated with flood-prone diseases. Floods can contaminate water supplies and lead to outbreaks of things like cholera, typhoid, and other waterborne illnesses. Preventing floods reduces this health burden.
Trying to put a dollar value on avoiding a cholera outbreak, that must be incredibly challenging.
It is. These economic analyses involve many assumptions and valuations that can be debated. But they're essential for making rational decisions about massive public investments in flood control. It forces a comparison between the cost of action and the cost of inaction.
It really shows that managing water is as much about economics and societal values as it is about engineering. One last management tool the sources mention is flood forecasting.
Yes, crucial for saving lives and property, even with defenses in place. Forecasting provides warnings. It involves both short-term prediction, hours or days ahead, and longer-term outlooks.
How does it work today?
It's very data-intensive.
Yeah.
Modern forecasting uses weather radar to track rainfall in real time, meteorological satellites to monitor storm systems and atmospheric moisture. This feeds into complex hydrological models. Ground networks collect continuous data on rainfall amounts, soil moisture levels, which affects runoff, and critically, real-time river levels or stages at various points along the river network.
So combining weather prediction with real-time river monitoring?
Exactly. Integrating all that data allows forecasters to predict how the river is likely to respond, how high the crest will be, and when it will arrive at different locations. This information is then issued as warnings to emergency managers and the public, hopefully giving them time to prepare or evacuate.
Okay. We've journeyed from the tiniest rill, figured out stream order, classified rivers, explored how they shape the land, and wrestled with the immense challenge of controlling floods. Let's wrap up our deep dive by looking at the river's final destination, its mouth.
Right, where the river meets its end, flowing into another, larger body of water, a lake, or most commonly, the ocean. And this is where we see the culmination of the river's sediment transport work, resulting in major depositional landforms. We need to clearly distinguish the two main types.
We already touched on the alluvial fan, right? That happens before the river reaches a standing body of water. It's when the steep mountain stream hits the flat valley floor on land.
Correct. That sudden velocity drop causes deposition on land, forming that characteristic fan or tone shape made of coarse sediment.
So the fan is terrestrial. What's the big one that forms in water?
That's the delta. A delta forms specifically when a river enters a large body of standing water, an ocean, a sea, or a very large lake. As the river water flows into the still water, it loses velocity very rapidly, essentially dropping its entire remaining sediment load.
Capacity drops to zero, everything settles out.
Pretty much. This deposition builds outwards from the coastline, creating new land. Think of the classic examples: the Nile Delta, the Ganges-Brahmaputra Delta, the Mississippi Delta. These are vast areas built entirely by the river.
Are all deltas the same shape?
No, their shape and dynamics are influenced by a constant battle between three forces: the amount of sediment the river delivers, the energy of waves and currents in the receiving basin, ocean or lake, and the tidal range. If the river deposition is dominant and wave tide energy is low, you get a classic bird's foot delta like the Mississippi, with long distributary channels building far out. If wave energy is high, the waves rework the deposited sediment, smoothing the coastline and forming beaches and barriers, creating a more rounded or arcuate delta shape like the Nile. If tides are strong, they can push sediment back into the distributary channels, creating funnel-shaped estuaries and linear sand ridges like the Ganges-Brahmaputra.
So it's a constant push and pull between the river dumping sediment and the ocean lake trying to move it around.
Exactly. Deltas are incredibly dynamic environments. Sediments might get washed away quickly by coastal currents, keeping the delta relatively small, or they might accumulate rapidly, building sandbars and new land, often shifting position over time.
Shifting position, you mean the river mouth moves?
Oh yes, deltas evolve. The main path of the river feeding the delta can change over time. A delta we see today might be just the latest phase, built on top of or next to older, abandoned delta lobes. We call these paleodeltas.
Old deltas.
Yeah. The Mississippi River is a prime example. Over the last, say, 10,000 years, the main outlet of the Mississippi has shifted dramatically multiple times, occupying and abandoning at least 6 major delta complexes along the Gulf Coast. The river finds a shorter, steeper path to the sea, abandons its old route, and starts building a new delta lobe elsewhere. The landscape is a map of this history.
Wow. So the coast is constantly being rewritten by the river.
In deltaic regions, absolutely.
And one final feature often found near river mouths, sometimes related to deltas, sometimes distinct.
And the estuary.
Right. An estuary isn't primarily a depositional feature like a delta, but a zone of mixing. It's typically a semi-enclosed coastal body of water, an inlet, bay, or gyre, where fresh water flowing out from a river mixes with salty ocean water brought in by tides.
So the brackish water zone.
Exactly. Estuaries are defined by that gradient from fresh to salt water. They're often incredibly productive ecosystems, serving as nurseries for many marine species, but they represent that transition zone, the final handshake between the river system and the marine environment. Okay. That brings us beautifully full circle. We started way upstream, defining the system, assigning stream orders, and classifying rivers, remembering that crucial difference between influent rivers losing water to the ground and effluent rivers gaining water from it.
Then we got into the mechanics, the river's toolkit. Capacity versus competence, how much it can carry versus how big a piece it can move. And we followed the life story of a meander, from the scrolls marking its pass, through the chute cutoff, to the formation of the Oxbow Lake, and eventually the Sealing Clay Plug.
And then the big challenge, floods. Understanding recurrence intervals, distinguishing between the standard project flood for typical design and the maximum probable flood for those high-hazard dams. We saw how engineering solutions like levees and channel cutoffs have complex, sometimes counterintuitive consequences, demanding that rigorous, difficult economic justification.
It really highlights the complexity.
I think the essential takeaway for you listening is that a river isn't just a line on a map or a passive feature. It's a dynamic system. It has immense power. It's constantly changing, but often in predictable ways if we understand the processes. And it demands really careful, integrated thinking when we plan our cities, our infrastructure, our agriculture, especially when we choose to live on its fertile, flat, but inherently risky floodplain.
Which leads us right into that final provocative thought. Floodplains are attractive places, right? They're flat, the soil is often rich, historically great for farming and building cities. They were built by the river depositing sediment during floods. So humans naturally gravitate there. But the river will flood again. It needs that space periodically. So when we create these fully developed floodplains packed with homes and businesses, we commit ourselves to this ongoing, incredibly expensive battle. We have to build massive levees, maybe channelize the river interventions that, as we've seen, can have negative consequences elsewhere and require constant maintenance and upgrades.
The cost of fighting nature's cycles.
Exactly. So the thought to leave you with is, what's the true long-term cost, economic, environmental, social profit of developing and then defending these high-risk areas versus adopting maybe wiser regulations? Maybe zoning certain areas for uses compatible with occasional flooding like parks or agriculture, maybe even in some cases strategically yielding the most vulnerable land back to the river to enhance overall system resilience. It's a fundamental tension between human development patterns and the river's natural dynamics, a tension that's only likely to intensify as our climate becomes more volatile. Where do we draw the line between protection and adaptation?